Alright, so this is example 1. I like this example because it's got a lot of features in it that cover the concepts of this module pretty well. I'll assume that you've read this problem, that you've tried to work this problem out on your own already, and I'm just going to work through the solution and highlight sort of the important points about the solution. So the problem describes two conducting spheres, but they are of unequal sizes. We've got the first conducting sphere has a radius of 2 centimeters, the second conducting sphere has a radius of 4 centimeters. I'm not going to use the numerical values for the calculation. Let's just call the two radii R1 and R2. Each sphere has some amount of charge on it. Let's just call that charge Q1 and Q2. So we've got two spheres, they're conductors, they have charge on them. They're brought into contact and then they are placed a distance 10 centimeters apart from surface to surface. So that means if we were to measure the distance between the surfaces, that is 10 centimeters. Let me call that D. So I'm going to use these symbols for the calculation, but keep in mind that Q1 in this case is the 10 nanocoulombs for the first sphere. R1 is the 2 centimeters for the first sphere. Q2 is the negative 2 nanocoulombs, R2 is 4 centimeters, and then this distance is 10 centimeters. So we need to calculate what the force exerted on the second sphere is. So we're looking for the force exerted on this sphere. Now the force is a vector, of course. We can calculate what the magnitude of this vector is, but we also need to make sure that we know what the direction of that vector is. So the charge that is on the two spheres is going to distribute over the two. So when we bring these two spheres into contact, that's not a very good drawing, but when we bring these two spheres into contact, then they basically become a single conductor. And the total charge then is going to distribute over the conductor. And the total charge is just the sum of the charge on both before we bring them into contact. So in this case, we have to account for the negative sign. In this case, the total charge is going to be 8 nanocoulombs. And that 8 nanocoulombs is going to distribute itself over the surface of the large sphere and the small sphere. So to start this problem, let's just assume that we're given a simpler problem. Let's say that we're told that we've got two spheres, they have different sizes, and they have different amounts of charge on them, and we need to know what the force that is exerted on one of the spheres is. So if we had that problem, then we would go about calculating the force using Coulomb's law. So we would say that the magnitude of the force is going to be Coulomb's constant times the charge on the first sphere times the charge on the second sphere divided by the distance between the spheres squared. Now the important part here is that this R is the distance from center to center. So when we use Coulomb's law, we have to calculate the distance from center to center before we can calculate what the force is. So that's important. And then the Q1 and the Q2 are the charges on the first and the second spheres. So really what we need to do is we need to figure out what is the center to center distance between the spheres, and then what is the charge on each sphere. So the center to center distance is fairly straightforward. We've got the surfaces are separated by a distance d, and then from the surface of the first sphere to the center is just a distance r1. That's just the radius, and the same is true for the second sphere. So that means that the distance from center to center after we place them apart is the radius of the first plus the distance between the surfaces plus the radius of the second. So that's the distance that we're going to have to use for Coulomb's law. The hard part, or the not as easy part, is calculating how much charge is on each sphere. So the way that we do that is we think about the properties of conductors, and we use what we know about conductors and charge to sort of figure out how much of this charge is going to be on sphere 1 and how much is going to be on sphere 2. So we know that the total charge must be conserved. So before we bring them into contact, charge 1 plus charge 2 is equal to sum total, and that's the 8 nanocoulombs in this example. After we bring them into contact, each sphere is going to have a different charge, but let's just call that Q1 prime and Q2 prime. So Q1 prime is the charge on sphere 1 after it's brought into contact with the second sphere, and Q2 prime is the charge on the second sphere after that. But we know that the sum of Q1 prime and Q2 prime is going to have to be equal to the total charge, just as the sum of Q1 and Q2 was equal to the total charge. So we know that this is true, and we know that this is true. And this Q1 prime and Q2 prime are the charges that we would use in our Coulomb's law. So the force then is going to be K Q1 prime Q2 prime over the distance between the centers squared, which would be R1 plus D plus R2, quantity squared. So now we got to figure out what Q1 prime and Q2 prime are. And the way that we do that is we consider what the properties of a conductor are. When we've got the two spheres that are in contact, we basically have a total charge Q distributed over a total area let's just call it A total. So I've got some charge on here. Let's say it's positive. And I know that it's going to uniformly distribute itself over the surface of the two spheres as a single conductor, because charge on a conductor will uniformly distribute itself over the surface of the conductor. It tries to basically the charge is trying to get as far away from the other charge as it can, and the best way to do that is to uniformly distribute over the surface. So if I've got a total charge Q sub t that is distributed over a total area A sub t, I can just say that the total charge is Q1 prime plus Q2 prime, and the total area is A1 plus A2. And the area of a sphere is 4 pi r squared. So that means that A1 is 4 pi r1 squared, and A2 is going to be 4 pi r2 squared. So I've got a total charge Q1 prime plus Q2 prime over a total area, which is 4 pi r1 squared plus 4 pi r2 squared. Now we start thinking about the ratio of charge that is on each sphere. So I've got the little sphere, the big sphere. This has an area A1, this has an area A2. This has some charge Q1 prime, this has some charge Q2 prime. The charge on Q1, the charge on the first sphere over the total charge, so this is what fraction of the total charge is on the first sphere, is going to be equal to the area of the first sphere divided by the total area. So that ratio should be the same. All right, if the area of the first sphere is 10% of the total area, then 10% of the total charge should be on that first sphere. So this is how we're going to calculate what Q1 prime and Q2 prime are, because I've already got now that Q1 prime is equal to A1 over A total times Q total. And I know that A1 is 4 pi R1 squared, and I know what the total area, surface area of the two spheres is as well. It's 4 pi times the squares summed. Right, and then I've got the total charge, and that total charge, I'll write as QT right now, but we already know that it's the sum of the charge that we started out with. Right? It's the sum of Q1 and Q2 unprimed that is going to give us that total. So this is what Q1 would be, and Q2 will be something very similar. So Q2 prime, sorry. That's going to be A2 over area total times the total charge. And if we look here, we've got 4 pi in the top and the bottom, which means that those are going to cancel. So this is going to be an R2 squared over R1 squared plus R2 squared. So the denominator is the same, and then I've got this QT again. Alright, so we've got Q1 prime and Q2 prime. We already know what the distance between the centers of the two spheres is, so we now are ready to construct Coulomb's law. The magnitude of the force is going to be Coulomb's constant times Q1, which is r1 squared over the sum of the radii squared times q2, oh excuse me, there's going to be a total charge here, times q2 all over the distance between the centers squared, which is again going to be r1 plus d plus r2, and that quantity is squared. So we're almost there. We're going to try to do a little bit of simplification as well. We do need to replace the qt's, right? We don't have qt given to us in the problem, but we do know that qt is just q1 plus q2. So I'm going to insert q1 plus q2 for the qt, and then I'm going to try to simplify this expression a little bit. So I've got Coulomb's constant out front. If I look at the numerator is going to have Coulomb's constant, this r1 squared, a t or a q sub t, this r2 squared, and another q sub t. These denominators I can put down here in the denominator with the r squared. So this will be a k r1 squared, r2 squared, the qt squared, which is q1 plus q2 squared, and then all of that over r1 squared plus r2 squared times the distance between them squared. So there we are. If I want to calculate an actual value for this magnitude, I need a number for q1, I need a number for q2, I need a number for r1, I need a number for r2, and I'm going to need a number for d. So Q1, as stated in the problem, is the 10 nanocoulombs. So that's going to be 10 nano, oh, that should be a capital C, 10 nanocoulombs. Q2 is the negative 2 nanocoulombs. That means that the total charge is going to be 8 nanocoulombs. That's going to be distributed over these two spheres. R1 is the 2 centimeters, R2 is the 4 centimeters, and then they are placed 10 centimeters apart. So this is the magnitude of the force that is exerted on sphere 2. It's actually the magnitude of the force that's exerted on sphere 1 as well. The force exerted on the two spheres is going to be the same. And we should note that since the charge on both spheres is going to be positive in this case, it's whatever the charge is, we know that it's going to have the same sign. If this was negative 12 nanocoulombs, then the total charge would be negative 2 nanocoulombs, and that would be distributed over both spheres. But whatever the case is, we know that the two spheres are going to have the same sign on charge, so that means that the force is going to point away from the first. Because they have the same sign of charge, and like charges repel. So there we have it. That is the force that is exerted on the second sphere. We had to use the fact that, well, we had to understand that the Coulomb's law has a distance squared in the denominator, and that distance squared is the center-to-center distance for spheres. It's not the surface-to-surface distance. We had to use the fact that we know that charge on a conductor is going to uniformly distribute over the surface of that conductor. When we bring two conductors into contact, the charge is going to uniformly distribute over the surface of the two conductors as if they were a single conductor. We use the fact that the total charge is something that will be conserved. So the total charge on the first and second sphere before they're brought into contact has to be equal to the total charge on the two spheres after they're brought into contact. And we use the fact that the size of the two spheres is going to determine how much charge ends up on the two spheres. And that's it. That's example 1.